Now let's look at how to graph a piecewise defined function. So when you're graphing a piecewise defined function, the first thing you want to do is identify any change of behavior values. Change of behavior values is places where things change in the domain. For example, the one that we looked at above, the cell phone, things changed at 60. So if you look here, we were one function between 0 and 60, and we were a different function when we were larger than 60. So the change of behavior value is going to be found in the domain, and it's where things change. Then what you want to do is you want to plug in the change of behavior value into every single function and determine out what the y value is. And those points you want to plot on your graph. Now you're either going to plot them as open circles or closed circles, and that's going to depend on whether it's included or not included. Remember, you're included if you have n or equal to, and you're not included if you don't. Then what you want to do is you want to graph the equations using either transformations of functions like we learned in the section before, or you graph them from what you know about lines. So they're either horizontal line, a vertical line, or you're looking for slope and y-intercept. But you have to make sure that the graph will only appear where the domain states it exists. So just like we did, or what we looked at for over here, remember I said I can't extend this line over here past 60 because the equation, remember, f of x is equal to 75, so that horizontal line only existed between 0 and 60. Past 60, I had to use this equation. And again, I can't extend this line this way because, again, this only exists where I'm bigger than 60. So we had to make sure that we graph these only where they exist. Let's take a look at the first example. So step 1 was to find the change of behavior value. So where are things changing? Again, this is my domain right here. Well, it looks like things are changing at the x value of 1. So I need to figure out what happens at 1 in the top equation, and then what happens at 1 in the bottom equation. And we're going to plot those points on the graph. So I'm going to go ahead and look at plugging in 1. If I were to plug in 1 to this top equation, it would be negative 1 plus 1. Well, negative 1 plus 1 is 0. So in this top equation, when x is equal to 1, y is equal to 0. Right, well, let's take a look at what happens in the bottom equation. Again, we're going to plug in a 1 down here. Well, 1 squared minus 1 is 1 minus 1, which is 0. So in the bottom equation, when x is 1, your y value is 0. So let's determine which one of these is a closed point and which one is open. Well, this has an or equal to bar, so that would make this a closed circle, and the bottom one does not, so that would make that an open circle. Let's go ahead and plot those points. So I'm supposed to have a closed circle at the point 1, 0 right here, and an open circle at the point 1, 0. Well, aren't those the exact same point? If you have an open and a closed circle at the same point, it's just a closed circle. Again, if it's open and closed at the same point, then you're just closed. So it just happened to be that we get the same value in the top function for 1 that we do in the bottom function for 1. And if that's the case, and one's closed and one's open, you just stay as closed. Okay, so that was step 1. Again, we identified the change of behavior value. Step 2, we found all the y values and put them on here with open or closed circles. So we've done the first, we've done the second. Step 3 says to graph each equation, but only graph it where it appears. So only graph it in its specified domain. So let's look at the two equations that we have. So we have the top equation, and the top equation is f of x is equal to negative x plus 1. Well, the top equation, f of x equals negative x plus 1, well, this is just a line, and we know that we graph lines using mx plus b, or my slope-intercept form. So I need to identify what is my slope and what is my y-intercept. Well, my slope for this particular function is negative 1 over 1, and my y-intercept is 1. So I can graph this top function as a line because I know how to do that. So let's go ahead and graph it. So my y-intercept is 1, and my slope is down 1 and then right 1. So let's go down and right. So down 1 and right 1. Just happen to be at that point. And then 2 points is all I need to make a line, so I'm going to go ahead and make my line. Now notice I made the whole entire line. Well, that's not correct because it says make sure you only graph it where the domain states you can graph it. So let's look at that domain. The domain of the top function says you can only be graphed where x is less than or equal to 1. So again, here's your x-axis. So here's 1 on your x-axis, 2, 3, 4. Here's 0, here's -1, -2. Where are the values on the x-axis less than or equal to 1? Well, over here on the left. So my line cannot exist to the right of that red dot. So the only place that blue line can exist is over here to the left of the red dot. And the reason for that again is that its domain says it can only exist to the left of 1. Well, here's 1 on my x-axis, so I can only exist to the left of 1. Well, let's look at the bottom equation. Well, the bottom equation is f of x is equal to x squared minus 1. Well, this is a transformation of the functions that I learned in the previous section. So I have to identify what type of function is it. Well, my function is a square function, so it's the one that looks like a U. And it typically has key points to the left and the right, both in the same direction. Well, do I have a horizontal shift? Is there something that I'm having in here in parentheses with x that's getting squared? No, so I write 0. Do I have a vertical shift? I do. I'm going down 1. So the new vertex, knowing that I have a horizontal shift of 0 and a vertical shift of down 1, is 0, -1. Then what's my compression stretch? Well, the compression stretch is the number, again, I'm multiplying out here. There is no number, so I can write 1. There's no need to find the x-intercepts for these. So that's all I need. Let's go ahead and plot this bottom equation with the transformations that I know. So first I go to my new vertex. Well, my new vertex is here at 0, 1. I'm going to make a dot. Then my key points, I'm supposed to go up 1, and then remember we're always over 1, and this one, since it's to the left and the right, I need to go up 1 and to the right 1, up 1 and to the left 1. So if I were to draw the entire equation, it would look like this. But that is not correct. It is not correct. Why is it not correct? Because I'm told that the bottom only exists to the right of 1, or where the numbers on the x-axis are greater than 1. So I don't exist to the left of 1. To the left of 1, I'm this blue line. I only exist to the right of 1. So everything that's over here to the left, I have to erase. I have this as my function. I just want to point out one last thing before we get to the next example. Notice that the change of behavior value acted as a boundary from one equation's graph to the other equation's graph. So the change of behavior value acted as a boundary from one equation to the other. That will always happen. So that's why I want you to find where the change of behavior value is located and plot it on the graph, because you know that, okay, well, only one of them is going to exist to the left of that, and only one of them is going to exist to the right of that. Okay, let's look at example 2. Example 2 is f of x is equal to the absolute value of x if x doesn't equal 0, and f of x is equal to 2 if x is equal to 0. Piecewise defined function. Step 1, find the change of behavior value. This is my domain. Where do things change? Well, it looks like 0, right? Things change at 0. So I have to figure out what happens in the top equation at 0, and I have to figure out what happens in the bottom equation at 0. So let's plug it into the top equation. Well, what's the absolute value of 0? The absolute value of 0 is just 0. So the top one has the point 0, 0. Okay, well, what about the bottom one? Well, the bottom one, well, that's just a horizontal line, right? There's no x to plug that in. So no matter what x I try to plug into this function, my y value is always going to be 2. So there I have that when x is equal to 0 for my bottom equation, y is equal to 2. Great. What kind of points are there? Well, this is not equal to, so that means that it has to be open. This has an equal to sign, that means that it has to be closed. So let's go ahead and graph those 2 points. I have an open circle here at 0, 0, and a closed circle at 0, 2. Now again, I need to graph each equation over its specified domain. So the top one is f of x is equal to the absolute value of x. Well, this is one of my basic shapes. Again, it comes from those transformations of functions. What does this one look like? Well, that's the one that looks like a V. And it's got key points again in the same direction, one to the left and one to the right. So let's figure out if we have a vertical shift. Do we have a vertical shift for this function? No, I don't. There's no number that I'm adding out here. Do I have a horizontal shift for this function? Again, no, I don't. There's no number that I'm adding in or subtracting to x inside the absolute value bars. So the vertex for this is going to stay 0, 0. What is the compression stretch? Well, the number I'm multiplying out here, I don't have one, so I just say that that's 1. So let's go ahead and graph this equation knowing that. So again, here's my vertex 0, 0. I leave that as an open circle because it needs to be open. Then my key points tell me that I need to go up 1, left 1, up 1, right 1. So I go ahead and I draw in that V. And then I have to pay attention to my domain. The domain says, all right, well, this function exists everywhere except where x is equal to 0. So that means I can exist to the left of 0 and I can exist to the right of 0. I just can't exist at 0. So for this particular function, I don't have to erase anything because that's exactly what I drew. All right, well, let's figure out for the bottom function. Again, the bottom function is f of x is equal to 2. Well, this is just a horizontal line, right? Y equal 2 is just a horizontal line through 2. So if I were to draw in that horizontal line, that's what it would look like. But is that correct? Well, let's check. No, it's not, because this only exists at 0. So this line only exists at one spot, at the point 0, 2. So I have to erase everywhere where I don't exist, because again, that equation can only exist over its specified domain. So it was only supposed to be that dot that we had originally put there. So this graph here is the graph of my f of x equals the absolute value of x if x doesn't equal 0, and f of x equals 2 if x is equal to 0. The next video is going to have some more examples of graphing piecewise defined functions.